Okay, problem 8.10. We're given a quadratic function f that has this term and this term together as the quadratic term. Then we have the linear term, and also we have a constant term. And a and b here are unknown, and it's something that we want to figure out. Our idea is to find the range of them. So the first question is to write f as a multivariate quadratic form. That means the matrix form. So because you see the 3/2 here, and you also have 1 plus a for the interaction term, that's how we form this matrix. And then again, to convert this into the standard form, we need to add this matrix and its transpose. That's giving us this. Okay, so that's a, and this is just a plus a transpose, which is our q. Okay, so that's our q matrix. And then there's also 1/2 in the front, and the rest are simple. Right, it's just a linear term, and this is a constant term. Okay, so apparently the b doesn't affect or the property, the main property of this f, because it's just a constant shifting this function f. But given this, we can answer the second question. It says that what is the largest set of values of a and b such that the unique global minimizer of f exists. For quadratic functions, the unique minimizer exists if and only if this Q matrix is positive definite. In other words, both of the eigenvalues of this Q must be strictly positive. So we just need to see how the eigenvalues of Q can be expressed as a function of A. Apparently, it only depends on A; it doesn't depend on B at all. So how do we express it as a function of A, and see in which case, for what values of A, these eigenvalues are strictly positive. Okay, so we have the Q matrix, as we said here, and then find the characteristic polynomial of this Q, which is just calculating the determinant of lambda I minus Q, and we'll get a polynomial of lambda. So that is the lambda I minus Q. And then we simplify this, we'll get that. Okay, and I break the parentheses here, we'll get this lambda squared minus 6 lambda plus 9, and then we'll combine the 9 and this term, which is supposed to be a constant. So I combine them. Now, what are the roots of this polynomial? For quadratic polynomial or polynomials of degree 2, the roots have a closed form, right? So that is the closed form. Okay, just negative of this, negative of negative 6 plus minus negative 6 squared minus 4 times this, and the denominator should be 2. So we can simplify this. You can see that 36 and this 36 will cancel. We have 4 times 1 plus a squared, and we have 6 outside, and we have 2. So the 4 can come out, becomes 2, and then we have 3 plus minus square root of squared 1 plus a. That's just giving us the absolute value of 1 plus a. So now you can see apparently 3 minus the absolute value is a smaller one between the two, right? So we just need this one to be strictly positive. So 3 minus 1 plus absolute value of 1 plus a is greater than 0, and then you just solve for this, and you easily get that a is between -4 and 2. Okay, so that is the range for a, and it doesn't matter what b is. So as long as a is in that range, then the function f has a unique minimizer. So the last question is, suppose we use this fixed step size gradient method to find the minimizer of f. Then the question is, what is the largest set of values of a and b supposed to be? Okay, for this algorithm to be global convergent. So that means the 2/5 should be within the range of 0 and 2 over the lambda max. Okay, so that is the requirement. So we just need to figure out what are the values of A corresponding to this lambda max. So we need alpha to be smaller than 2 over lambda max, and we set the lambda, the eigenvalues of Q is 3 plus minus 1 plus A, absolute value of A 1 plus A. So the larger one should be 3 plus the absolute value of 1 plus A. So this should be just that, right? So we just need to figure out what are the possible values of A such that this inequality holds. And again, you can see this, we just need the 2 over 5 less than that, and you can do a simple algebra and to show that this essentially is the 5 should be bigger than that, or 2 must be bigger than the absolute value of 1 plus A, and then you can solve for that. By the way, I think I didn't mention here either, but you know how to solve this. It's just if the 1 plus A is less than 3, that means 1 plus A should be between negative 3 and 3. And then you subtract 1 on both sides. You get that. Okay, same thing for here. Same thing for here. And you can easily get that. So that's the range for A, so that the fixed steps gradient method with the step size alpha over 5 can guarantee a global convergence.